we are going to have a presentation from Sandra Schmidt, project manager at RWE. So Sandra will give us a presentation on the RWE activities and research on carbon capture, and specifically on the activities that were carried out on the demonstration site in Germany in Niederaussem, and also the applications of these technologies in recent RWE projects. So with this, I'd like to give the floor to Sandra, thanking her for the presentation for today, attending our meeting and presenting. And I would kindly ask all of you to make sure you're mute so that we are not encountering any issues. So thank you, and please, Sandra, the floor is yours.
Thank you very much. Yeah, welcome to the presentation. And let's talk about the projects of RWE Power regarding CO2 capture. And yeah, currently we are developing a CO2 capture project at the Knappsacker Hügel in Hürth near Cologne. The aim is to separate biogenic CO2 from the flue gas of several sewage sludge incineration plants there. This CO2 can be stored or used after transportation by rail and ship. And yeah, this results then in negative emissions, which means that the CO2 is sustainably removed from the atmosphere. The results and experience of our R&D activities are being integrated into this development of the project at the Knappsacker Hügel. In particular, the results of the 15 years of operation of a CO2 capture pilot plant at the Innovation Center in Niederaussem. In the following, I would like to present some of the research projects at the pilot plant. I will explain how they have helped to minimize the technical and economic risks, and how the carbon capture technology can develop further in the future. Since 2005, RWE has built up a lot of experience on carbon capture plants that were operated with industrial power plant flue gas. The first experience with carbon capture at power plants we gained in 2 European funded projects, the projects Castor and CESAR, with a pilot plant in Denmark. This plant was operated with different amine solvents. One of these developed solvents in this project were CESAR1. And nowadays, this is very often used in research projects and also in the carbon capture pilot plant in Niederaussem. At the same time, RWE was involved in a pilot and a demonstration plant in the USA with the chilled ammonia technology, where ammonia was used instead of amines. This was the first time in the world that CO2 was captured, and at the same site, it was stored in the underground directly under the power plant. In 2013, the carbon capture technology of Shell Kanshof was also tested in UK at RWE. The heart of RWE's R&D activities for carbon capture and storage is the carbon capture pilot plant in Niederaussem. A 10-year cooperation with Linde as a plant constructor and BASF as process and solvent supplier began in 2007. All aspects of the technology were investigated and optimized. BASF now offers the resulting OS Blue technology commercially. The special feature of Niederaussem is that we are able to operate there the plants for 24/7. This means that long-term tests have carried out that are unique worldwide. Test times of several 10,000 hours without replacing the solvent are beyond the reach of other test plants. This is why the pilot plant has served as a test platform for many international research projects since the end of the cooperation with Linde and BASF, so since 2017, such as Line, Launch, Scope, Medora, and Drive. Niederaussem also offers unique testing options regarding the composition of flue gas and the CO2 quality. A wide range of flue gas specifications can be adjusted and the effects of special trace substances can be tested. Even if the flue gas source is a lignite-fired power plant, the results can be transferred to a wide range of applications such as biomass power plants, sewage sludge, and waste incineration plants, or even gas-fired power plants. While the first 10 years of research focused on energy optimization using new solvents, the focus of more recent research is on the effective minimization of emissions and waste streams. This is directly related to solvent management, like the minimization of solvent degradation. In the DRIVE project, the effects of maximum capture rates are being tested. CO2 quality is important for both storage and the use of CO2, which is why it is part of the research program in Scope and Medora. Because of the existing compression and liquefaction plant at Niederaussem, not only the CO2 quality can be analyzed, but also several CO2 utilization options were tested in the past. The CO2 scrubbing pilot plant in Niederaussem is designed as an all-rounder. This means that it can deal with both fast and very slow reacting solvents, which can have a high or a low CO2 load capacity, and which can behave very differently regarding emissions and degradation behavior. Various process steps can be bypassed so that an optimized operation mode can be configured for several boundary conditions. With a CO2 production capacity of 0.7 tons of CO2 per day at 90% capture rate, the plant is large enough to deliver suitable process data for simulations or scale-ups to large plants. And at the same time, it is small enough to avoid needless high costs for operating and equipment. The process is equipped with online measurement technology to evaluate the process performance, but also the test of the measurement technology itself. The parts of the plant marked in green are the emission reduction technologies. Like the FGD, so the flue gas desulfurization unit with an wet electrostatic precipitator, the aerosol test module, the flue gas conditioning system, the dry bed here in the absorber, the water wash section, and the acid wash section. This all is used for emission reduction tests. The blue part, the absorber, is used for the CO2 capture, and the parts of the plant marked in red are the desorber, the reboiler, and the head condenser are used for the regeneration of the solvent, which means to boil out the CO2 out of the solvent so that the CO2 leaves the plant in a gaseous form. The large number of emission reduction process steps already shows that costs can be significantly reduced by the right knowledge about flue gas and solvent behavior. Ammonia is the most important volatile degradation product of amines. Depending on the concentration and the maximum allowed limit, it must be separated from the CO2 lean flue gas in a so-called acid wash. The Medora project is testing whether the formation of ammonia can be significantly reduced using an innovative membrane technology in the solvent. The membrane is used to separate the flue gas oxygen, which is dissolved in the solvent before the solvent enters the hot parts of the plant. The aim is to halve the oxidative degradation of the amines. Removing the oxygen from the solvent also has the advantage that the product CO2 also contains less traces of oxygen, which means that costly post-cleaning steps can be cancelled. The lower than 10 ppm O2 limit in the CO2 product, what is mentioned here, comes from the quality requirements for CO2 transport and storage of the Northern Light project. Typical capture rates for carbon capture plants using amine solutions as CO2 solvent are 90 to 95% for energy demand reasons. However, the regulatory reasons or when negative emissions should be achieved, higher capture rates can have advantages for economic reasons. In the DRIVE project, the effect of highest capture rates of more than 98% on the performance of the carbon capture process are being tested. Last year, a capture rate of 99.8% was achieved. What is shown here as one example. We reached 321 ppm. This was the CO2 concentration in the CO2 lean flue gas, what was given to the atmosphere. And this was around 100 ppm lower than the CO2 concentration is in the ambient air at the moment. This means that CO2 that entered the power plant process with the combustion air was also captured. The specific energy demand for the regeneration of the solvent in this test was only approximately 30% higher than with normal capture rates. However, emissions and solvent degradation have not been analyzed sufficiently. We need long-term test operation with this highest capture rates, and this is the reason why this technology is not yet being used commercially. Test campaigns such as the one in Niederaussem must first show the entire technology can be evaluated in all its facets. Four partners from 6 countries are involved in the SCOPE project. The consideration of all facets of sustainable operation of CO2 capture plants is the central theme of SCOPE, starting with the possibilities of avoiding emissions through the necessary measurement technology to the evaluation of the effects of emissions. For this, test campaigns are being carried out at 6 different carbon capture plants in Niederaussem with CESA1, at waste-to-energy plants in the Netherlands, at a research plant in Norway, and at 2 other plants in India. The test data are used to validate simulations of emission formations, of solvent degradation, of atmospheric chemistry, and also of dispersion modeling. At the Niederaussem plant, data on emissions and the performance of emission reduction technologies were determined. In long-term tests, the influence of the aging of the solvents, the CO2 capture rate, of the oxygen content in the flue gas, and also of the influence of load changes and short-term plant shutdowns were investigated. The pilot plant in Niederaussem offers excellent boundary conditions for the investigation of such emission reduction technologies. This slide shows more than 20 interconnection options for the various emissions reduction process steps which are available in Niederaussem. In addition, around 285 online measurement systems and a large number of sampling points are available for data collection. In infrared spectroscope and a measuring system for determining the particle number concentration and size distribution for particle diameters between 6 nanometers and 5.4 micrometers are used to investigate emissions from carbon capture plants. An important factor for the level of emissions is the particle concentration in the flue gas before the CO2 capture section. It is important to understand the difference between vapor pressure-driven and aerosol-driven emissions. Aerosol-driven emissions can be a factor of 100 higher than vapor pressure-driven emissions. We have extensively investigated the effect of individual and combined emission reduction systems for both types of emissions. For CESA1, a simple water wash is not sufficient to achieve the desired low emission values. Nevertheless, tests with only the water wash are important to investigate the effects of process parameters on the emissions, such as the capture rate or the flue gas composition. The diagram on the left shows that the emissions of CESA1 of the CESA1 component AMP increased slightly with the increase of the CO2 capture rate, while the concentration of the second amine, piperazine, and that of ammonia remain stable. The 2 diagrams on the right show how the emission behavior changed when the CO2 concentration in the incoming flue gas is reduced from original 15% to 5%. The reduction in the concentration was achieved by adding air, so that at the same time there's a corresponding increase in the oxygen concentration from 5 to 15%. Emissions actually fall at lower CO2 levels, which is due to the temperature effects in the absorber. When less CO2 is available, less reaction heat is released, which lowers the temperature in the absorber, and this means, in this way, it lowers the emissions. An example of a very effective emission reduction technology that can also be used to control aerosol-related emissions is shown here. The so-called dry bed development in Niederaussem, which is commercially available as OA's aerosol technology. The diagram on the right shows that particle size distribution, once with and once without the operation of a wet electrostatic precipitator. With operation of the wet electrostatic precipitator, the particle concentration at the inlet to the CO2 capture plant is over 1 million particles per cubic centimeter, shown here with the red curves. Without operation of the wet electrostatic precipitator, the concentration is in the range of less than 10,000 particles per cubic centimeter. These are the blue curves. The diagram on the left shows the effects of the number of particles on the emissions. In the pink and blue areas, the number of particles in the incoming flue gas is very high due to the wet electrostatic precipitator was switched on. This leads to high concentrations of amine emissions due to the aerosol formations. The blue curves show the amine component AMP, and the red curves show the amine component piperazine. The emissions are shown that at the top, and the concentration in the circulation water of the water wash section are shown at the bottom. The water wash section is used to clean the CO2 lean flue gas before it is released to the atmosphere. The green curve is the ammonia emission caused by the solvent degradation and its vapor pressure driven emission. In the blue area, here, you cannot read it, it's very small, maybe. So in the blue area, the dry bed was also operated. The positive effect can be clearly seen in the emissions and is confirmed by the amine concentration in the circulating water of the water wash. The green area at the end shows the effect of switching off the wet electrostatic precipitator without using the dry bed. This also significantly reduces emissions, but not as significant as the downstream process step of the dry bed technology. Both systems have, if you look at the green line, both systems have little effect on the vapor pressure driven emissions of ammonia. Depending on the application, the dynamic or start-stop behavior of the CO2 capture process in interaction with the flue gas source is important. This applies not only to the CO2 capture rate and the heat demand, but also to the emissions. To date, it was not been possible to simulate such processes with sufficient accuracy. Real data from pilot plant tests, therefore, are the best basis for predicting plant behavior for industrial applications. As can be seen here from the operation data of the CO2 capture plant in Niederaussem, the operating parameters stabilize within few minutes. The results and experience gained from the 15 years of operation of the CO2 capture plant at the Innovation Center in Niederaussem being used. They will flow directly into the CO2 capture project currently being developed by RWE Power at the Knappsacker Hügel. The plan is to capture around 200,000 tons of biogenic CO2 per year from the flue gas of 4 sewage sludge incineration plants. Here you can see the first draft for 2 CO2 capture units on the left side of the rails, and the CO2 processing, liquefaction, intermediate storage and the rail connection for loading the liquid CO2 to wagons on the right side. An optimized solvent and process technology will be used at the Knappsacker Hügel, which offers clear advantages based on the experience gained in Niederaussem. Optimized processes with a stable and highly efficient solvent has the advantages that less steam is required to regenerate the solvent, and that waste streams and emissions are significantly reduced. In addition, the optimized emission reduction technology is used so that a maximum reduction of emissions can be achieved with minimum effort. We plan to submit the permitting documents for this plant in about a year. Yeah, the experiences gained in the 115,000 operation hours of the carbon capture pilot plant in Niederaussem, and the knowledge gained from 20 years of participation in CCUS projects are not only helpful for optimization of the technology itself, but also for supporting all steps of the project development and the implementation of such a plant at the site. This means that in addition to the minimization of solvent consumption and emission, assistance can be provided with issues relating to the integration into the site, permitting, negotiations with the technology providers, and also the operation of the plant itself. All in all, the experience gained from research and development serves to minimize the risk of investment and operating costs. Our knowledge will also be used in other CO2 capture and storage projects planned by RWE Generation in the Netherlands and also in UK. Yeah, last but not least, we would like to thank all of our funding bodies and project partners for the many years of good cooperation. And I would like to thank you for your attention. Do you have any questions?
Thank you, Sandra, for your presentation. Very detailed, I think. So I would propose to open the floor ended for question and answers. So I already see the first raised question, raised hand. So please feel free to ask any questions that you may have. Floor is yours. Yes, Abad, please feel free to speak.
For the nice. You can hear me?
Yes, we do.
Yeah.
Thanks a lot for this excellent presentation. CO2 capture is a very nice topic, and everyone is interested in it. And I see that you have already started 2 projects in India. Can you tell us a little bit about the economical impact? Is it worth investing in that also for countries where the economic plays much bigger role than, for example, here in Germany or in Netherlands? So what's the economical impact? Why it is interesting for countries in Middle East or in Africa, or when will it be interesting? Thanks a lot.
We cannot save the climate only in Germany or the Netherlands, or only in Europe. So at the topic of CO2 capturing and the different possibilities for CO2 capturing, I would say the whole world is working on it. not only India, but also China, Australia, Japan, USA. Yeah, they are working on economic issues, topics. Yeah, but nevertheless, they are interested in this climate protection.
Perhaps
Thanks.
if I may add, because I was also involved in the scope project, I can say that the Tuticorin site, where you see quite a lot of CO2 is captured, this is connected for utilization. So they produce chemicals out of it. And yeah, this is depending on the regulatory framework. And yeah, certificate prices or taxes on CO2, it is for some sites already today interesting, but again, it is always depending on the boundary conditions. And if we talk about billions of tons of CO2 that we have to capture and remove, also from avoid the emissions, we have to find out for what we can use it and for where we have to store it.
Thank you for your question and also answer. So I see Han. Please, Han.
Yeah. Thank you very much for this detailed presentation. So I saw that you demonstrated a very high capture rate. I understand that it was with CESAR-1. What was the strategy to achieve such a high capture rate? For example, if you increase the energy, the regeneration duty, so what were the strategy that was put in place to reach this capture rate? And would you say that you can conclude that such high capture rate is achievable with CESAR-1 without major impact on CapEx or OpEx, or is it something that still need to be further investigated, and whether you have planned to confirm this very high and good value?
So we need to investigate it more, because there's a lot of stress for the solvent if you reach such high capture rates. What do you have to do to reach such high capture rates? You have to increase the solvent flow rate of the circulation of the flow rate. You have to increase the steam for boiling the solvent in the net desorber to reach very low lean load concentrations, and all this stresses the solvent, and how many what is the degradation rate of a solvent in such operating behavior, and how can you deal with it, and what does it mean for the emissions? These are topics what need to be analyzed for a long time. And this is the reason why the long-term tests in the DRIVE project are ongoing.
Okay.
But nevertheless, it is a direct concurrence to direct air capture.
Thank you. So I see the next hand from Andreas Schmidt. Please, Andreas.
Yes, hello. Very interesting with the slides. I wanted to ask about this membrane you showed on the earliest slide. Do you need some additional pressure to push it through this membrane? And is this an innovation that comes directly from RWE, or
It is not a development of RWE. We are testing this module, which comes from Peter. You can help me?
Yeah, it's a patent from TNO in the Netherlands.
TNO.
And regarding the gradient that you need to push the oxygen out of the solvent, you will have the sweet gas. So this could be nitrogen or even CO2. And then you will have, perhaps this will be tested as light vacuum. So a little bit of under pressure. What's the optimum? We will find out. So there are 18 months of testing planned of the technology. And as Sandra has pointed out, we need long-term testing. CESAR1 is a low degrading solvent. It mimics, we think, also the modern world of new commercial solvents. And then you need time to find out what are the effects. And in the laboratory, you see the numbers. This was reached with this setup. And we will do it with 100% of the solvent flow in the pilot plant.
So, but this equipment is still in in construction, so not implemented in the process until now. So the project
it works with under pressure, not with over pressure. That is very interesting.
Yeah, under pressure on the gas side. So no, in the membrane. So you have the normal pressure of the
solvent comes from the outside, and then under pressure
and the under pressure in the sweep
retrieve
gas. Yeah.
Very cool.
Might be mid of the year that it will be presented at the Trondheim conference, if you're interested. Because it's also not just tested at RWE, it will be also tested at a waste-to-energy plant in the Netherlands. So from HVC, and there we will find out what we will achieve.
Yeah. Also the aging of this membrane here when it comes to 1 year operation and so on. Yeah, very interesting. Thanks.
You're welcome.
So before we go to the next question, we just launched a questionnaire now on Slido for the quality of our webinars. So feel free to provide feedback to our webinars via these 3 questions. That will help us improve the quality for the future. So I see happily some other questions. Han, do you have other questions? Please feel free.
Yes, thanks. I found there were quite a big focus on emissions, and I think it's interesting because you benefit of such so many hours of operation to address these questions. And I noticed that it's interesting with the lower CO2 concentration, emission seems to be also lower. My question was related to the CESAR1. Nitrosamines used to be a big hot topic in the past. Is it something that you looked at, or that what are your view, especially for solvents such as CESAR1, and especially if you have the view in 4% CO2 concentration flue gas?
I don't know if I get everything. So nitrous amines. Nitrous amines are a topic all the time, and we have to look at it all the time. For example, because of work safety reasons. This was the first question. The second one was low CO2 amounts. What were your questions there?
When you, I don't know if you did the test of CESAR1 in 4% CO2, and the conclusion is it that it is better in terms of emission? And for example, especially with CESAR1, can you say that there is no risk of nitrosamine formation, or should be looked after still for this kind of application?
Okay. So the reason why the lower CO2 content means that there's a lower lower emissions is that the temperature in the absorber is lower because there's less reaction in the absorber. So it is an exotherm reaction, no? The CO2 with a solvent, which means that the temperature increases in the absorber from above 40 degrees Celsius to above 75 degrees Celsius in normal operation with the 15%. And this is much lower if you only have in the same absorber only 5% CO2. And this means that you have lower vapor-driven emissions. Nevertheless, you have a higher oxygen content. Yeah, and Peter, I don't know the results. What is the result of the higher oxygen content on the degradation products and so on the ammonia concentration?
I think we have operated around 6 weeks, so really a step-like function, you can say, and we have not seen really a big effect. So there's also
you see it here in the green line.
Yeah.
No? The ammonia doesn't increase. Yeah.
Okay.
So I might also add, I think there's this topic also regarding nitrous amines. To be honest, what is emitted is very, very low emissions. There special equipment from Sintef was used also in a campaign to make analysis, and the results were also compared with Impinger method. So also scrubbing out whatever comes via the depleted flue gas, and compare then this with mass spectroscopy methodologies with another sampling method, it's very low. But to be honest, the discussion is today another one. It's more amines are emitted and reacting with nitrogen oxides in the atmosphere. And I think also in the scope project, detailed this also models on atmospheric chemistry have been used to analyze what are the emissions, what reaches the ground, and we at the moment we can say even under the estimation of waste, under worst case scenarios, so running all the time, all amines are reacting with NO2. They all form a very dangerous nitrous amine, which is not so true. But even if you estimate all this, the emissions, so that you can say the ground concentrations are lower than what than limits defined at the moment. So from our point of view, really environmental benign.
Thank you for your responses. So there's an additional question from Christophe. Please.
Yeah, thank you for the presentation. I have actually two questions about CESAR1. So the first one is about nitrous amines as well, but I wanted to know if you have any NOx abatement as a pretreatment before the capture unit. And my second question is regarding the degradation rate of the CESAR1. I would like to know what were the best operating conditions or best approach to have the degradation rate as low as possible. Thanks.
So we have tested if it makes sense to reduce NOx before the flue gas enters the CO2 capture plant, and we haven't seen any changes in the emissions or in the solvent degradation by reducing the NOx amount before entering the flue gas to the absorber. And what was the second question?
The second question was about degradation rate of CESAR1 solvent. I wanted to know what are the best approach. Is it to use DORA system or to have other kind of solvent management system, or maybe by having specific operating condition? How you can reduce the degradation rate of the solvent?
A very complex question. Yeah, Peter.
Perhaps I might help. So there's also a publication on the way, but on this topic stressing CESA1 solvent. So perhaps I think Sandra mentioned it. We have not seen what others have published on the effect of NO2 on nitrous amine formation or this very hard degradation, so that it oxidizes quite a lot. We removed more than 80% of NO2 specifically by thiosulfate scrubbing as a pre-treatment, and we have not seen an effect. So on nitrous amine formation and also on degradation. Then regarding what is now the best approach for solvent management and to minimize degradation, I think Sandra mentioned first, okay, one parameter is higher temperature. Yeah, higher temperature is stressing all solvent. So reducing this is always good, but this is then directly linked to the capture rate and the performance that you also want to achieve. Then we have tried effects of active carbon and also particle filters in the solvent loop. Just to explain it, we have also operated the plant more than 1 year without active carbon filter and without a particle filter. We have not seen an effect. We have used ion exchange to remove degradation products, and this is also then perhaps a difference to some mantra perhaps on how capture plants should be operated. We have seen that cleaning the solvent, so we remove between 80 to 100% of contaminants, the heat stable salts, so the organic acid residues, but also inorganic trace components. And then we found out that you can achieve this. This is good. You remove inactive compounds from the solvent, but we saw a doubling of or by a factor of 3 higher degradation rate of the solvent. So it seems that keeping the solvent clean, this is one philosophy, might be not the best one. And this is a part, also this what we found here at Niederaussem will be investigated further in coming research project. Just to explain why is there this old philosophy? I think that to clean it is always in the past it was linked on work in the laboratory for monoethanolamine, and there was the basic estimation that iron, especially and other metals, catalyze the degradation, and I have to remove it. If not, you will see degradation. Then you have these organic acids. The inventory will be becoming more corrosive, and then it attacks the walls of your absorber. You will have dilution of more catalyst, and then you have a self-accelerating process. But we have not seen this link of degradation to iron in our pilot plant, and you should always keep in mind that the reactivity of metals and dissolved metal ions in the solvent depend on the solvent matrix. There are no free metals. They are all complex by water, by amines, and the degradation products. So the redox potential of this potentially as catalyst acting stuff in the solvent depends also highly on the environment, and this must be taken into consideration. I could also just simply say follow the principle of Le Chatelier, removing degradation products from the solvent would push the equilibrium to more degradation. And finally, just also to underpin this, when we used an anion ion exchange resin, goal is to remove anions from the solvent. We could remove around 30% of the iron from the solvent. This is a clear sign that there's not just a cationic iron available, but a negative charged iron complexes are in the solvent. So, and we are, let's say, far away from a complete understanding what's going on, but our conclusion from that is I don't say operate your plant with a dirty solvent, but with a cleanest solvent might be also not the best solution. There we need more work to better understand where's really the optimum. So you had a complex question and I had a long answer, but perhaps you might understand. But there are also quite a lot of publications on this topic. You will easily find when you Google.
Thank you, Peter.
Thank you, Peter, for your exhaustive answer. We still have 7 minutes. I saw 2 questions on the chat and the raised hand by Jens Walter. So I would first give the floor to Jens and then go through the comments in the chat if we still have time. Jens, please.
Yeah, thanks. Only a short question and maybe a short answer. What's your experience with high gradients in the exhaust mass flow? Have you tested that, and what's the result? Thanks.
High gradients in the so in the flue gas at the inlet?
Yeah, right.
Okay. So, for example, start-stop behavior, and yeah, we have tested at the pilot plant. Nevertheless, if you have yeah, a high fluctuation flue gas, the amine process itself is very robust. You can save energy if you are able to regulate the flow rate of the solvent circulation as function of the flue gas amount and also as function of the CO2 content in the flue gas. Nevertheless, the curve regarding the specific energy demand is has a very so if you have a too low solvent flow rate and tries to keep your capture rate stable, you need a lot of more steam than if you have a too high solvent flow rate. So if you operate all the time at a little bit too high solvent flow rate than the optimal point, then you can deal with fluctuations of the solvent and the CO2 content. Of the flue gas and the CO2 content in the flue gas.
Thank you.
Thank you, Jens and Sandra. We still have, maybe we can take this question, Sandra. So, Kulban Singh, BLD, wrote, can you make a comment about compression capability required for this technology, flow rates, discharge pressures? So what happens to the CO2 which comes out of the plant?
It depends on what should be done with the CO2. So yeah, if you have the connection to a pipeline, to a CO2 pipeline, then you have to yeah, need the conditions of the pipeline. If so, in this project, what we are developed at the Knappsacker Hügel near Cologne at the moment, we will transport the CO2 liquefied by wagons. And this means that it will be cooled and pressurized to about minus 25 degrees Celsius and 20 bars. But there are at the moment discussions with the wagon suppliers and also with the intermediate storage sites at the coast, and also with the transportation via ship. So you have CO2 ships with different CO2 conditions, so low pressure, medium pressure, and high pressure ships. We are at the moment developing the project for a low pressure transport line, but this means that you have to increase the pressure at the storage site at the inlet. And maybe if you calculate the whole way, maybe it's better to increase the pressure and transport us with medium or high pressure vessels. But this is in calculation. You have to look at each single case and what possibilities you have and what will be your storage site, what will be your transport facility, and your possibilities to connect to a pipeline or the possibilities to use it. No? If you have a usage, a synthesis unit, maybe you do not need liquefied CO2 but gaseous CO2, then maybe you need it only by 10 bars. Then it would be easier to have not the steps to a high pressure or to a liquefaction of the CO2.
Thank you, Sandra. So we can maybe take a very last question, but shall be very concise, please. So I see the raised question from Hamide Ahi, and for those just providing the written comments, they can also get in touch with ETN office, who will get in touch with Sandra with their questions. So feel free to contact us. So Hai, please, please, the floor is yours. Thank you.
So Sandra, thank you very much for the great presentation. So you have over 15 years of operational experience, and during these 15 years, you have tested different technologies as well as different solvents. And at the end, for the Knapsack project, OS technology and solvent has been selected. You highlighted the benefits of OS technology with the dry bed, for example, but if you also give a comment on OS solvent, if you compare that with other solvents, what are the benefits of this solvent? That would be great.
The benefits of the solvent is the very low energy demand and the stability of the solvent regarding degradation, and this combined with very low emissions. So these are the big benefits. The biggest of these benefits is the energy demand, because the special boundary condition at this site is that we do not have a lot of steam on site, what is not used in other processes, so that we have to make our own steam, and this is expensive, and therefore one of the reasons why we have here a focus on a very low energy demand.
Thank you.
Thank you, Sandra, and thank you, Hamide, for your question. So we propose to close the webinar at this time, as we just are at 12:02. So first of all, just to let you know that ETN will upload both this presentation on its website and also the recording of this webinar on the YouTube channel. And if you have any further questions that you would like to forward to the presenter, please let us know, write us an email, and we'll get in touch with Sandra. So with this, we would like to thank Sandra and her team for the presentation at today's webinar, and also you all for attending today's webinar. And we hope to see you soon again at our next episode in spring 2025. Thank you very much, and we wish you a good day. Thank you.